Let's consider a particle moving along a straight line whose position is described by, well, what I call a position function. Now, for me to differentiate the position of this particle really gives me the velocity of the particle. So the velocity is nothing more than the derivative of my position function. And the acceleration is just the rate of change in velocity, which is the second derivative of the position function, or first derivative of the velocity function. So let me ask a few questions. What's going to happen at the values of t, which is 0, as these linear factors for velocity? Because I think when one or two of these factors is equal to 0, the velocity is equal to 0, and I'm at rest. Well, the particle is at rest. And so I think the particle's at rest at t equals -1/2 and t equals 1. Now, notice if t is between -1/2 and 1, this is negative. So the velocity being negative means I'm moving in a leftward direction. Outside that interval, to the left of -1/2, but to the right of +1, I'm moving in the rightward direction. As a matter of fact, I could probably draw a picture of this. Let's suppose this particle is moving along this number line. Now, I think at t equals -1/2, something interesting happens. But if t is equal to -1/2, can we compute the position real quick? I don't know what it is. My apologies. Maybe I should have done this. Is that this? So at t equals -1/2, the position is at 4.25, and the particle changes from moving to the rightward direction to moving in the leftward direction. Now it changes direction again at t equals 1. So here, when t is equal to 1, I'm at a position of s being equal to, don't know, 1, 2, is that -4? See, here's what I have so far. I have, as t increases all the way to -1/2, I'm moving in the rightward direction. As t ranges from -1/2 and 1, I'm moving in the leftward direction. But beyond t being equal to 1, I'm moving in the rightward direction again. You can get that just by building a sign graph for your velocity function. Again, a 9th grade algebra sign graph. Plot the two zeros. Check these 3 subintervals, because these two numbers subdivide the real number line into 3 subintervals. If t is a billion, plug in a billion for t here and here, both these are positive. The product is positive. If t is something like 0, there's a negative times a positive times another positive, that makes it negative. If t is a -billion, there's a positive times a negative, that's positive. And so clearly, I'm moving the rightward direction over this interval for t, leftward direction, rightward direction. Now, I think likewise, you can build yourself a sign graph for the second derivative function, the acceleration function. Plot at 0, test intervals. If t is a billion, positive. T is -billion, I'm negative. What this really means is it says that my velocity is increasing after t equals 1/4, and the velocity is decreasing to the left of it. So next on my list, what are interesting questions can I ask? Let's do this. Next question. At t equals, how about 2? Let's talk about the velocity, and let's talk about the acceleration. Well, with these computations, it's as easy as just plugging 2 in for t. Any one of these 3 versions of my v of t, how about the last one? And at t equals 2, my acceleration is this. Now, if s is measured in meters, t is measured in seconds, then I guess this is measured in meters per second, and this is measured in meters per second squared. Can I ask us some more sophisticated question? Let's do this. Now these are t values. Now as t increases -1 to -1/2, I'm moving in the rightward direction. From -1/2 to +1 for my t values, I'm moving in the leftward direction. Then from 1 to 2, I'm moving in the rightward direction again. So I think to come up with the answer to my question, I need to compute these distances. I shouldn't say distances. Can I back up? I need to first compute these positions. Now I'm afraid I'm wasting a little bit of time. So I think I've computed some of these already, but I forgot their values. So very quickly, -1. Well, that was easy. -1/2 is the one I should have remembered, and I don't. Shoot. Oh, I've computed right here. Now I'm kind of worried. Do you mind if I just double check the arithmetic? At -1/2, I might have computed incorrectly. Jeepers. So I think this number right here is wrong. My goodness, off to such a great start. And let's see, S eval at 1 appears I've computed. I'm so nervous. I'm going to check that real quick. So at -1, or excuse me, positive 1, 2. Looks good. Now, +2, I think it's going to give me, whoops, a big number. Well then, to answer my question, let me give myself a tad bit more room. I think the distance traveled over that time interval should be broken up to 3 parts. From -1 to -1/2. Then over this interval for t. And lastly, over this interval for t. But these are distances, so these are positive values. So from -1 to -1/2, the difference in terms of positive value is this. Assuming my arithmetic's correct. Please double check that. But now over this interval, excuse me, I know it looks like this minus this, but in reality, I'm just taking the absolute value of the difference. So how about just going from this minus that, just to make my arithmetic easier? That gives me 6.75. Now the positive distance traveled from 1 to 2 for t values is going to be positive, actually not +5, it's going to be +13. And so I think the total distance traveled over that time period is really that. Well, maybe that was a bit too physics-oriented instead of the natural sciences, but at minimum, I do need you to understand that the first derivative position function is my velocity function. The second derivative of my position function, which is same as the first derivative of my velocity function, is my acceleration function.